the last couple of lectures, I spoke about position representation, where we dealt with function spaces. In particular, we spoke about L2 of A, B, and functions in this space are functions of a real variable x, and they satisfy the condition of square integrability d cubed x dx, whatever, within that region of integration is less than infinity. So, this is the function space that we are interested in, and we introduced the position basis. It is a continuous basis, and functions psi of x in the Dirac notation are represented in this manner. There is a very logical reason why function psi of x is really this inner product, and therefore psi star of x is represented in this manner. Now, in this function space, wave mechanics is structured, and the Schrodinger equation really pertains to the behavior of the wave function psi of x, which describes the state of the system, an abstract ket psi represented in the position basis, and that is called the wave function. So, basically in this lecture I wish to continue with the Schrodinger equation and the concept of stationary states. So, the Schrodinger equation. So, there we are, and we stopped at a point where we said that if psi were a function of x and time, and this is in one dimension, one space dimension, for a free particle moving in one dimension, a free particle of mass m, we had this equation, and this allowed for plane wave solutions. So, basically psi of x t was of the form a cos kx minus omega t plus b sin kx minus omega t, where the momentum p was h cross k. There was an energy E of the particle given by h cross omega. And since in classical physics for a free particle we would have started with this equation, the analog in quantum mechanics is to replace E by the operator IH cross delta by delta t and P by the operator minus IH cross delta by delta x in one dimension. And therefore, when I put hats on these two objects and write E as IH cross delta by delta t and P as minus IH cross delta by delta x, I get this equation. This is called the classical quantum correspondence at the level of replacing energy and momentum by their respective operators. This is first order differential operators. Now, suppose I have to generalize this equation, the Schrodinger equation, to 3 dimensions. I will now have psi as a function of r, where r has 3 components x, y and z in Cartesians. And since P itself is minus IH cross del, the differential operator here is replaced by del squared. Where you had delta by delta x, you now have del squared. So, this is the equation for a free particle of mass m moving in 3 dimensions. It is free, therefore, there is no potential term. Now, suppose there were a potential term. Let us go back and look at how we got this. In classical physics, the total energy would be the kinetic energy plus the potential energy. This is in the position representation. So, the potential is going to be a function of x in 1 dimension, for instance. And therefore, if I now put in this potential and write the Schrodinger equation for a particle of mass m and momentum p subject to a potential v of x, I have the following. Now, in 1 dimension, psi of xt, and that is all there is to it. Of course, if I have to write the Schrodinger equation for a particle in 3 dimensions subject to a potential, straightforward. Del squared now. So, that is what we have. So, this is the Schrodinger equation for a particle subject to a potential V. It is a function of R. For the moment and for quite a considerable part of the course, I would assume that this potential is a real function of space, because if the potential had a complex part, that would correspond to the presence of sources and sinks, and that class of problems is not what I wish to consider now. Now, given this equation, I can see quite a bit happening from here. First of all, psi is complex. Let us go back to the 1 dimensional case. Schrodinger equation. Particle subject to potential V of x. Psi is complex in general. So, I have the following equation, and then I have an equation for the complex conjugate, which reads minus IH cross delta psi star by delta t. This is minus h cross squared by 2m delta 2 by delta x squared psi star of xt. V is real, and therefore, I have this equation. Explicitly, there is an I that is occurring, and in that sense it differs from the diffusion equation. Otherwise, there is a correspondence between the Schrodinger equation and the diffusion equation, but there is this I that is present there and that is the speciality of the Schrodinger equation. In general, all solutions psi or psi star cannot represent the state of the system, the instantaneous position being given by the value of x at a given time taken on by the time parameter t. Psi has to satisfy certain boundary conditions, and it is clear that since we are looking at systems where the probability of existence of the system is 1 and mod psi squared is the probability density, and we require this between the limits of dx to be 1, that is the total probability to be 1, it is clear that the wave function psi and therefore psi star have to belong to L2, to the space, to the linear vector space L2, the space of square integrable functions. Now here I can do the following. I can pre-multiply this by psi star and this by psi. Then the first equation becomes IH cross psi star delta psi by delta t. I could do it in 3 dimensions if you wish, and therefore let me just do it in 3 dimensions. I would not write the argument r of t minus h cross squared by 2m psi star delta 2 psi by, or del squared psi now, because we are in 3 dimensions, plus psi star v psi. That is my first equation. The second equation, I can just multiply this by psi, and I have minus IH cross psi delta psi star by delta t is minus h cross squared by 2m psi del squared psi star now plus psi v psi star. That is my second equation. Now remember that psi is a function of x, scalar function of x, and so is v in the position representation. For instance, if you looked at a potential which is quadratic, like in the case of the oscillator, v is half m omega squared x squared, and therefore v of x, v would normally have been an operator, but since this operator x is merely identity times x, v is half m omega squared, the number x, x squared, times identity if you wish, but I am going to suppress that, and I just write v as half m omega squared x squared. The point is that these objects commute in general, and therefore if I subtract 2 from 1, I have IH cross psi star delta psi by delta t plus psi delta psi star by delta t is minus h cross squared by 2m psi star del squared psi minus psi del squared psi star, and these two terms, the potential term cancels out. I can always write this as delta by delta t of psi star psi, that takes care of these two terms, is minus h cross squared by 2m IH cross, and that just gives me a minus h cross by 2m I, which gives me an IH cross by 2m. So I have an IH cross by 2m psi star del squared psi minus psi del squared psi star. This is what I have. Now this looks like a continuity equation, because I can bring this to the other side, and I have delta by delta t of psi star psi minus IH cross by 2m psi star del squared psi minus psi del squared psi star equals 0. Define the quantity S, which is a vector, as minus IH cross by 2m psi star del psi minus psi del psi star. It is a 3-dimensional vector. It is a vector under rotations in 3 dimensions, because the gradient operator has a vector sign on top of it, and then this equation simply becomes plus del dot S equals 0, because del dot S is minus IH cross by 2m. If you expand this, it is grad psi star dot grad psi plus psi star del squared psi minus grad psi dot grad psi star minus psi del squared psi star. And then these two terms cancel out, giving me what I want there. And therefore, with this definition of S, I have a continuity equation delta by delta t psi star psi plus del dot S equals 0. This object is strictly positive. Its modulus of psi the whole squared. In one dimension, integral psi star of x, psi of x dx. In Dirac notation, that is identical to integral bra psi, a complete set of states ket x bra x. That integral gives me identity ket psi dx. Returning to the continuity equation, I have delta by delta t psi star psi plus del dot S equals 0. This object is called the probability density for very good reasons, because when you integrate over it, you get the total probability, integral psi star psi dx, psi star of x, psi of x dx integral. That is the total probability, and that is 1. And this object here is called the probability current density. Because it is a vector. This is analogous to the equation that you might have seen when you did a course on electromagnetic theory, where given a static distribution of given a distribution of charges with charge density rho and current density j, delta rho by delta t plus del dot j was equal to 0, and that was the continuity equation that you had there. This is analogous to that, except that the interpretation here is that this object psi star psi is a probability density and this is a probability current density. You might recall that if you did an integration over space here, integral rho dV was the total charge, and you showed that the total charge was conserved. You would have shown in electromagnetic theory that the total charge was conserved provided certain boundary conditions were met. That is precisely what we are going to do in this context as well, because if you look at the continuity equation in this case, and do an integration over x or over the volume, because we are now doing it as a 3-dimensional problem, integral dV, that is the volume, plus integral del dot S dV, that is the elementary volume, that quantity is equal to 0. I can always pull this outside, and I have, since the integral is over the space, this I can use Gauss's theorem, and I can write this as a surface integral where d sigma is an elementary surface area, n is the unit normal, and S dot n is a component of S along the direction n perpendicular to the surface. So this quantity is equal to 0. The fact that the total probability that is the interpretation in quantum mechanics, the fact that the total probability does not change in time, that if you normalize the wave function such that the probability, the total probability is 1 at a given time, the total probability that the system exists does not change in time. That implies that delta by delta t of this quantity is 0, which means that this surface integral should vanish, and indeed it does because of the boundary conditions, because S is essentially psi star grad psi minus psi grad psi star, and since this is a surface boundary, this is the entire volume, the surface boundary is again at infinity. So the requirement is that the wave function and the derivative, the first derivative of the wave function, vanishes at infinity, space infinity. that will see to it that S vanishes sufficiently fast so that this term drops out, and I have delta by delta t of the total probability is equal to 0, which means that probability is conserved. The statement that probability, total probability is conserved holds for all instants of time. So that's what we see here, and therefore this automatically takes care of the boundary conditions for solving the Schrodinger equation. The boundary conditions are the following: the wave function and the derivative go to 0 sufficiently fast as at space infinity. So in one dimension, psi of x and delta psi by delta x, in one dimension they go to 0 sufficiently fast as x goes to plus minus infinity, and so on. So these are the boundary conditions. So when we work with the Schrodinger equation, it is really the fact that probability should be conserved, the total probability should be conserved, which gives rise to this boundary condition that the wave function vanishes at plus minus infinity, space infinity. If you are talking about one dimension, at x is plus minus infinity, and as x goes to plus minus infinity, the first derivative also vanishes, goes to 0 sufficiently fast. So given these boundary conditions, the Schrodinger equation can be solved because it involves a second derivative with respect to x, and I have two boundary conditions. So we can treat, in the case of the time independent Schrodinger equation, we can treat this as an eigenvalue problem. I will show you how to do that shortly. Impose these two boundary conditions, find the eigenvalues and eigenfunctions. We understand that if the potential is time independent, as is the case here, the case that I have been considering, there are some very interesting states called stationary states. Stationary states, or wave functions which behave like stationary states of the system, which represent stationary states of the system, satisfy the following property. First of all, mod psi squared, the stationary state psi, for instance, in one dimension, can always generalize it to 3 dimensions. Mod psi squared is independent of time. All expectation values of observables, relevant observables in the state psi are independent of time, they are conserved in time. And in general, if you have a stationary state of the system, if the system is in a stationary state, you will find that the energy levels are essentially partially discrete at least. It will not be a continuous set of energy levels. The energy spectrum will at least have some of the levels being discrete. Now, given this, I want to find out how exactly I get stationary states of the system when the potential is time independent. So let us look at the equation IH cross delta psi by delta t. Let us start with 3 dimensions. Is minus h cross squared by 2m del squared psi of RT plus V of R psi of RT. Let us see if it is possible to consistently separate psi into a space dependent part and a time dependent part. So we write the wave function psi of RT as some chi of R phi of t. Now, if I do this and feed this back into that equation, I have IH cross, the time dependence does not act on chi, that is my left hand side. The space derivative does not act on phi, And of course, I have plus V of r, chi of r, phi of t. Can divide throughout by chi of r, phi of t. And if I did that, the first term, the left hand side, is just this, does not depend upon the space coordinate at all. This is only dependent upon time. And as to the right hand side, plus V of r. Look at the right hand side, does not depend on time at all. Now, if the left hand side does not depend upon the space coordinate r, and the right hand side does not depend upon the time coordinate, time at all, time parameter at all, and these two are equal, it is clear that this is equal to a constant and that is equal to the same constant. I call that constant E. And then I have two equations. The first equation simply says IH cross delta phi of t by delta t is E phi of t. The solution to this equation is very simple. Phi of t is simply e to the minus IET by h cross. So that is all that I have, because the first derivative pulls out a minus IE by h cross. The h cross cancels, and with this I just get a plus. So I have an E phi of t. That is all that there is to it. Now, as to that, the right hand side, I have minus h cross squared by 2m del squared chi of r, multiply throughout by chi of r, plus V of r chi of r is E chi of r. So, depending upon the value of E here, depending upon the value of the constant, I am going to have a solution. So, I should really be talking in terms of a chi of r for a given value of E, and that is what we will have to solve for given this equation. Therefore, the total wave function psi of RT is some chi of r, which really depends upon the value of the energy that we have, e to the minus IET by h cross. The upshot of the whole thing is this, that if I now find modulus of psi the whole squared, it is clear that this term cancels out, and I just have modulus of chi e of r, which is just chi e of r whole squared. And even if it were in general complex, I could write it like this. So, this is what I have. So, that is certainly one property of the stationary state. Equally true that if I take expectation value of any operator in the state psi of r t, that is like saying psi star of r t, expectation value of some operator, let me say A, which is of course written as a function of r. We will have to write it in the position basis, psi of r t d cubed r, that is over the entire volume of integration. It is clear that this part has e to the IET by h cross, and the psi here has e to the minus IET by h cross, which cancel out, and therefore it is really like doing UE star of r, A of r, chi E star of r, A of r, chi E of r d cubed r, and therefore expectation values do not depend upon time. For all times I have the same expectation value. So, in a stationary state of the system, the time dependence goes as e to the minus IET by h cross, and this equation here, which one solves to find chi of r, clearly has no time dependence, and this is the time independent Schrodinger equation. So, the time independent Schrodinger equation can be written this way: minus h cross squared by 2m del squared chi E of r. that came from the potential, that came from the kinetic energy, it came from p squared by 2m plus v of r, chi of r, is E chi of r. I could drop the E, simply remember at the back of your mind that corresponding to, this is an eigenvalue equation, and corresponding to a given value of E, you have a wave function chi of r. And since this whole thing here minus h cross squared by 2m del squared plus v of r is a Hamiltonian, there is a potential energy part here and there is a kinetic energy part here. So this is merely the statement h chi is E chi. So it is an eigenvalue equation. These are the energy eigenstates written in the position representation, it is chi of r, and corresponding to the energy value here, the actual value of E, you have a chi. So if you have a set of energy levels, could call them E sub n, they are discrete, you have chi sub n of r, where n takes value 0, 1, 2, 3, etc. So corresponding to the energy value E0, there is an energy eigenstate chi naught of r, corresponding to the energy eigenvalue E1, chi 1 of r, and so on. So this is the eigenvalue equation that one likes to solve, and this is really the time independent Schrodinger equation, which is what we use when we deal with stationary states. Of course, if you put the time dependence, then you have an IH cross delta by delta t already coming in, and this kind of an analysis does not go through. So in a stationary state, if the system is in a stationary state, the time development is very simple and straightforward, simply moves as e to the minus iet by h cross, and then the part of the wave function that depends upon the position coordinates alone. Now the reason why I would be interested in energy eigenstates is obvious. As I have stated earlier, even when I did things in the abstract using matrices and column vectors, we are looking at conservative systems, systems where the energy is conserved during the motion of the system. So energy is a constant of the motion, and therefore the Hamiltonian becomes a very respectable operator. You would really like to choose as your eigenbasis or the basis states in the linear vector space, states which are the complete set of common eigenstates of all the constants of the motion corresponding to that situation. Energy is certainly a constant of the motion because we are looking at conservative systems, and therefore we will look at eigenstates of the Hamiltonian and any other observable which commutes with the Hamiltonian, in other words which is also a constant of the motion. So in general we are looking at energy eigenstates for this reason. Now in wave mechanics, the energy eigenstates are written in the position representation, and even if we look at a separable Hilbert space, there are a denumerable infinity of energy eigenvalues, eigenstates chi naught, chi 1, chi 2, etc., each one of them being written as a function of r, corresponding to which there is an energy eigenvalue E sub n. So you will recall that the whole problem started by saying that in classical physics I have this, and then replacing E by IH cross delta by delta t and P by minus IH cross del. We could do the same thing in relativistic physics. So let me digress and comment about what happens in relativistic physics. Take the expression for E in terms of the momentum of the particle and so on, replace E by IH cross delta by delta t and P by minus IH cross del. So this is a digression worth doing at this stage. In relativistic physics, I know that E squared is P squared C squared plus m squared c to the 4, where m is the rest mass of the particle, and I consider the particle with momentum p, linear momentum. C is the velocity of light in vacuum, and this is the expression for energy. E squared is p squared c squared plus m squared c to the 4. Now given this, I simply have to, if I want to do the quantum mechanics of an object which is traveling relativistically, then I take this expression and I write IH cross delta by delta t for E and minus IH cross del for P. So that gives me the following. So that is an E squared, and it is supposed to act on psi of RT because it has now become an operator in quantum mechanics. Is P squared, there is a C squared, so that is a constant which can be pulled out, plus m squared c to the power of 4 psi of RT. So that gives me minus h cross squared delta 2 psi by delta t squared, that is E squared psi, is equal to P squared c squared plus m squared c to the 4 psi. Therefore, I have delta 2 psi by delta t squared minus delta 2 psi by delta t squared. I divide by h cross squared well, I can certainly divide by c squared now, or a minus c squared if you wish. So if I bring the del squared to this side, I just have 1 by c squared delta 2 psi of RT by delta t squared minus del squared psi of RT is equal to or plus m squared c squared plus h cross squared psi of RT equals 0. That is the Klein-Gordon equation. That is a relativistic wave equation. For an object with rest mass m moving with momentum p, and the p has been suppressed because I have got an IH cross del replacing the operator p. So this is what I have. The reason why I brought this in, it is a digression to tell you that in all these contexts, simply take the classical expression for energy in terms of momentum, mass of the particle, potential and so on, replace the energy by IH cross delta by delta t, and the momentum, the linear momentum, by minus IH cross del if you are looking at 3-dimensional space, or minus IH cross delta by delta x in 1 dimension along the x axis. And then you get the corresponding equation, the quantum mechanical equation, which one is supposed to solve for the wave function psi of RT. That is by way of a digression. Now returning to the non-relativistic case, which is all that we will be looking at, I have the following. In general, I seem to have a situation h psi equals E psi. Look at this, minus h cross squared by 2m del squared plus v is the Hamiltonian acting on the wave function. In this case I called it chi, is E chi. So the formal solution for psi is e to the minus I h t by h cross psi of 0. So this is what I have. So let me look at the Schrodinger equation itself. IH cross delta by delta t psi is h psi, and therefore the solution is psi of t is e to the minus IH t by h cross psi of 0. Now one thing is clear, that if I give you psi at the initial time, whatever may be the initial reference time, I can find psi at any other later time without knowing the value of, without knowing what psi was at any time between 0 and t, All I need to know is the initial value psi of 0, and I can give you psi at any instant of time, later time. Do not need to know the value of psi at any time between 0 and the time of interest to me. So in that sense, this is a Markov process. There is no memory of the path that is taken, the manner in which psi changed with time, but merely the initial value, the value of psi at time t equals 0. That is a point worth bearing in mind. And now we will look at specific examples to see how we can solve the time independent Schrodinger equation. We are looking out for stationary states, and that is precisely why we got there. So we will substitute various values for V of r, start with the one dimensional problem first, substitute for V of x, and then get the eigenvalue equation set up and solve for the eigenfunction and the eigenvalues, energy eigenvalues and the eigenfunctions. The eigenfunctions are functions of position. We are working in the position representation. Clearly we should be able to match with what we did earlier for these systems. For instance, we have already worked out the eigenvalue problem for a one dimensional harmonic oscillator, and there we saw that the energy eigenvalues were of the form n plus half h cross omega, where omega is the angular frequency of the oscillator and n takes values 0, 1, 2, 3 and so on. Now here we would, for instance, work out the harmonic oscillator problem in the framework of wave mechanics, which means we solve for an equation like this in the position representation. And so we will substitute V of x in one dimensions. V of x is half m omega squared x squared. We should be able to retrieve the same form for the eigenvalue. We should be able to get hold of the eigenfunctions, and as we have seen earlier in other ways, the ground state for instance is a Gaussian function of position. We should be able to retrieve all those results. So the Schrodinger formalism is an equivalent formalism to what I have already done using abstract operators, and now I will illustrate the whole thing for the harmonic oscillator in wave mechanics, that is using the Schrodinger formalism. So one dimensional harmonic oscillator. So starting with a time independent equation, we have minus h cross squared by 2m, looking at stationary states of the oscillator. So the time development is simply e to the minus iet by h cross. So I have minus h cross squared by 2m d2 psi of x by dx squared, where psi is the wave function, plus half m omega squared x squared psi of x is equal to E psi of x. So we just have d2 psi by dx squared. So I can take this there and I just have minus 2m by h cross squared times half m omega squared x squared psi of x is minus 2m by h cross squared E psi of x. So that just gives me d2 psi by dx squared minus m squared omega squared by h cross squared x squared psi of x is minus 2m E by h cross squared psi of x. When you solve these equations, it is always good to find out what is the length scale, the natural length scale in the problem. You will recall that when I did this using the abstract operator method, I defined A and A dagger, the raising and lowering operators for the harmonic oscillator, and then we had X and P in terms of A and A dagger. And we realized then that root of m omega by h cross has dimensions of inverse length, and that is why we defined x in terms of A and A dagger, which were dimensionless quantities, as A plus A dagger, x was A plus A dagger by root 2 multiplied by an overall root of h cross by m omega. Similarly for P, because root of m omega h cross came out as a coefficient to take care of the dimensions of linear momentum. Now to solve these differential equations, it is good to scale out such dimension quantities. Find out the natural scale in the problem. In this case, it is a length scale. Find out the natural length scale and scale out. So you define an object rho, which is alpha x, and clearly rho is dimensionless because x has dimensions of length and this object has dimensions 1 by length. Then d by dx is simply d by d rho times d rho by dx, which is alpha, and d2 by dx squared is again alpha squared d2 by d rho squared. So we can now write this equation, recast this equation in terms of a dimensionless variable rho, and that is a good way of doing the problem. I do not have to keep track of m's and omegas and so on. They will appear naturally in the final solution of the problem, and a lot of things can be read off very easily by using dimensionless quantities when we solve the differential equation. This would be a general technique that we will use. We now have therefore psi of r, psi of x has now become psi of rho, and we have d2 psi of rho by d rho squared. That is the first term, but then there is an alpha squared multiplying it, minus the second term. This is an alpha to the 4 x squared keep it as x squared, we will take care of this later, psi of x, which becomes psi of rho. I have to write this also in terms of rho, which I will, because rho is alpha x, so x squared is rho squared by alpha squared. So I have that is equal to minus 2 me by h cross squared psi of rho. That is what we have. So divide throughout by alpha squared and you have d2 psi of rho by d rho squared minus rho squared psi of rho equals minus 2 me by h cross squared alpha squared psi of rho. So I define lambda, which is 2 me by h cross squared alpha squared. Now you can check that lambda is a dimensionless quantity, and then the equation itself becomes d2 psi of rho by d rho squared plus lambda minus rho squared psi of rho equals 0. So this is the equation that I have to solve, and the idea is to find out the value of lambda, the values that lambda can take, and the possible admissible solutions psi of rho. This is the manner in which we will approach the problem, and it is a good place to stop. We will take it up from here in the next class.